Hi everyone, David Blakey here. This video's topic is Python lists. And if you refer to the handout, Session 3 handout, that introduces lists in earnest, you'll see, of course, that it's a handout about containers. So lists are one of 4 containers that we looked at in Session 3. And there is a video devoted to each one. The beginning of the handout shows basic usage for each of the containers in turn. Constructing, adding and removing elements, and retrieving certain elements like through subscript or slice, and then looping through the container. This is what we do in computer science. We build up these different types of structures, these different containers, and then we either loop through them or we select pieces of them. File is not a container really, but it does act like one in some instances, and so we include it here. Of course, your homework involves opening up a file, reading it, selecting pieces of it, and then building up a structure, very basic operations that we do as programmers every day. So let's look at lists. I'm going to show you each of the types of operations. You can refer to the handout for syntax if it helps. Basically, I'm just going to show you how to create a list and then manipulate the list. And then one thing I also want to emphasize with all of these videos is that there are similarities between the containers that allow us to loop through them, get slices of them, and then test them with operators like len and in, or sometimes we call them built-in functions like len and in, that are similar across the board. And we'll see that, and you'll see that as you go through these videos. So constructing a list is quite simple. As you can see, a list is a container of other objects. These are all objects of a certain type, just like a list is. In fact, lists can contain other lists, but we'll get into that in a later session, slightly more advanced work. Here we have a list that contains 3 strings, 2 integers, and 1 float. Of course, it's possible for the object to be inserted by name instead of by actual literal value. You can see the first 6 of these are literal values that have been added into the constructor, the square brackets being the constructor, as literal values. But the last element, the last object here, Meister, is a string, which we assigned up here. Now normally we don't even create lists in this way, or oftentimes we don't. Most of the time we build up lists element by element from a data source. For instance, you might have a text file like the first example that we talked about in homework, and the text file might show you different pieces of strings that you want to insert into the list. And so you would loop through the file, split out the piece that you want, and then add it to the list. Adding is quite simple. If we had a variable named var and we wanted to append it to our list, we'd simply use the append method. Append adds to the list. If we were to append a literal, you could see that that's being done. And if at the end we print the list, and we go ahead and run the program, you'll see the result is everything that we initialized the list with, plus the 2 variables that we appended. Notice that when we print out the list, you don't see the name var or the name Meister, even though that's how they were added to the list. That's because when we place a label into a container, we're not actually placing the label there. We're referring to the object by putting the label there. That's how labels work. And in session 4, we'll talk more, well, really towards the end of the session 3 handout, but usually in the session 4 class, we'll talk about how these objects are referred to. They aren't actually in the code. Many times they're referred to just by their names, Meister, var. But if we were to append var into mylist, as you can see we did there, var is 5. If you look at the output, you can see that 5 appears there. It doesn't show you var. That's because var is just a label that points to it. And now the container is a container that also contains it. The integer 5 is the object, and it's now being pointed to by two different structures, one var and the other mylist. So we can put literals into the list, or we can put objects by name, by label as well. We're doing both, and there's really no difference to them. The only reason we have labels is because it's a convenient way to refer back. Well, it's really the only way we have to store an object and then refer back to it. Well, I take that back. Labels are one way, containers are another. Now the string A is referred to by mylist. We'll get into references a little bit later, but needless to say, if you want to construct a list in the code, you can use square brackets. You're able to use literal objects, and you can also use labels that point to objects. Anytime you see a square bracketed list, that is something with commas and what appear to be objects in between, you can know you're looking at a list. And many times, for example, if we go into the Python interpreter and you do a dir stir, which we've done a number of times in class, look closely at the very first character of the output after dir stir. You see a square bracket, then you see what looks like a string, and it is a string, and then a comma, then another string object. This is a list of string objects. In fact, it's all string objects, and that's our list. And the only reason we see a list there is that dir returns a list. It's designed to return a list. So now let's talk about, we've talked about constructing the list, and we've talked about appending to it, something we often do. Let's talk about getting things out of the list. That is, not removing them, but just getting values from the list. You know that mylist is this new long object that we have here, this long container that has all of these objects in it. And of course, I may not have explained that when you see a hash mark, anything after the hash mark is ignored on a line. So that hash mark is a comment that's designed for our use, and Python ignores them. In fact, the interpreter strips them out before even processing your code. Now let's remove, or actually let's copy out or inspect elements of mylist. I'd be interested in trying to pull out just the third element. That is the C, as you can see, the string object that is a C from the code. I'd like to print it. In fact, why don't I just assign it? I can say third L equals mylist2. As you know, as we've discussed, index numbers begin at 0. So A is 0, B is 1. C is referred to by the number 2. Now, a single subscript will get us back the object itself. I can print third L here. And I can also print the type of third L. Let's take a look at that. Well, I don't even have to run it. I can just tell you that this is going to be C, and the type of third L is going to be stir. Although when we run it, you'll see you get a slightly different output. Type stir. What we're getting back is really a type object that tells its type string. And that's what Python tells us when we ask for the type of this object. That's absolutely no surprise. The third object in my list is a string, and when we use a subscript to copy it out, what we're doing is not really copying it out, but we'll discuss references later. We're assigning that object to the third L label. Now the third L label points to the object as well, and so when we print it, we see it, and we can check the type. That gets us the string, just to confirm that we're getting back the object. It's also possible, using a single subscript, to do the reverse of accessing an element. You can instead update the value of an element. So if I were to say mylist2 equals xxxyx, I'm actually reassigning the value of the third element. Before, the third element was C, and we're now going to change it to xxxyx. We can print mylist2 to show that that's the case, and we can also just print mylist. We'll print mylist. We will change the element here, and then we'll print mylist again to see that the change has been made. So you can see that initially our list looked like this, and that after the change was made, the third element, that is subscript 2, reassigned to this string xxxyx, which is what we're expecting. So you can see that using a subscript, we can access the element. That is, if we were to say var equals mylist2, and we can reassign the element. It really depends on who's on the left and who's on the right of the equal sign. That's what makes it different. In this case, you can read this as var equals the value of mylist2. We can read it that way for right now. We'll read it slightly differently starting next week. But here we're just saying apply a label to the object that's in mylist2. That is 0, 1, 2, the C. So now var will be C. But here we're saying take the object xxxyx and take that value and now assign it or place it in the mylist container at subscript, at the third element at subscript 2. So we're reassigning in this way. And you just want to be able to read these two usages in that way. Clearly, when we say something equals something, it's going from right to left. The value is going from right to left. So if you say var equals mylist2, we're saying that the value of var is whatever the value of mylist2 is. We can say it that way. But in the next item, we're saying mylist2, whatever's in mylist2, whatever mylist2 is, it's equal to the value of mylist2. The value of the third element in mylist2 is this value. Now, similar to pulling out a single element, we can now pull out 3 elements, let's say, or 4 elements from this list. Why don't we say slice equals mylist. Why don't I take from the C, which is element 2, all the way to 3.5. Okay, interesting. Now pay close attention. This is element 2, right? We start with element 0, which is A, element 1, which is B, C, which is 2. Then we have 3, 4, and 5. Oh, I see I've made a mistake. If I wanted to get 3.6, I would put a 6 here. The upper bound is non-inclusive. We've talked about that. 0, 1, 2, 3, 4, 5, 6. The 6th element, or rather index 6, the 7th element of my list, index 6 points to hello. But interestingly, when we print slice, see what we get here. I'm going to add a print statement here just to clarify our output. Let's run that. See, we get our previous output, then a blank line, and then C 1, 2, 3.5. 4 elements, C, 1, 2, and 3.5. Looking at the index numbers again, 0, 1, 2 points to C, 3, 4, 5, 6 points to hello, but hello is not included. Hello is not included because the upper bound is non-inclusive. It's just the way it works. It's not terribly intuitive, but it is the way it works. And so it's the way we're going to work. Now my question to you is, what type of object is slice? What type of object is slice? Do you recognize it? I guess I don't really have to make it bigger, but I'm going to. By the way, if your YouTube video is a little fuzzy, you can switch to HD. If you switch to HD, it'll be sharp enough to put full screen on your monitor. 4 objects here, a string, an integer, and a float. But what sort of structure is this? It should be pretty obvious. That's a list, and you can tell it's a list because it starts and ends with a square bracket. It has objects in between, and the objects are separated by commas. And that's how that works. That's a list. So you can see that slicing of a list returns another list, which makes sense since we're looking for here 4 elements from the list. 4 elements from the list. And what other format could they come in? They could come in some other sequence, but it makes sense that a slice of a list should be another list. It's almost as if we took a knife and just cut it right here and said, here, let's just take that section out, put brackets around it, and make it into a list. So this slice results in this list here. And of course, that's true of slicing everywhere. We saw that with strings as well. When you slice a string, you get back another string. Even if we were to make one element, that would actually be kind of interesting. What would we get if we asked for 0 to 1? Now, my question to you first, with this slice, how many elements? It would just be the one element because we're starting at 0, which would be A, and we're ending before 1, which would be B, except that it's non-inclusive. So that would be one element. So the question now for you to speculate on is what type of object do you suppose slice will be now? Will it just be the one element, A, a string, or would it be a list with one element in it? Let's find out. Yes, it is a slice. It's a list with one element. So that's how slices work. It doesn't matter if you're selecting one element or not. If you wanted to get back the object itself, of course, you would use a single subscript, not a slice. Single subscript would just get us back one of the elements, in this case, the string. So great. Slicing makes sense, I hope. If it doesn't, you can always run this video back. Looping is just as important and something we should do. So I'm going to delete this, get rid of some clutter. And I'm going to say for element in my list, print element. Let's see what we get there. As you can see, we get each element in turn. A, B, C, 1, 2, 3.5. And then the value that Meister pointed to, which was hello, the string hello. Okay, looping is quite easy, and looping allows us to look at each element in turn, and it stops automatically when the last element is reached. You can do anything with an element, of course. Examine it, check it to see if it's of a certain type, if it's above a certain value, or whether it indicates that you should do an operation or something like that. We use looping through lists all the time. Let's look back at the handout. One thing we haven't discussed yet is removing an element, so let's do that. Something we would do less often, but it is one way to loop through a list. Sometimes folks want to remove an element from a list so that it can look at the element, deal with the element, and then move on to the next element and stop when the list has been exhausted. You can remove an element by using the pop function. Now, my favorite thing to do is to remove from the beginning. Usually we remove from the beginning if we're going to go through and exhaust a list. So I'm going to do that. Removed element 2 equals mylist pop 0. Removed element 3 equals mylist pop 0. Why do I have a 0 there? 0 refers to the element that I'd like to remove, 0. But why, if that's the case, and if I'm going to print removed element, why don't we do that? Print removed element. Print removed element. Print removed element 3. Whoops, that's what I meant to say, 2. Okay, so what are we doing here? We're removing an element and assigning that element to a new label. This is a little like using a subscript, except that the list is actually changed. In the end, I'll print my list to show it. Note that we're removing from the beginning 3 successive times. You might ask, why don't we remove 0, 1, and 2 if we're removing each of the elements? That's because once we remove it, the list contracts, and all of the, in this case, if we remove the first element, all of the other elements move to the beginning. So we're constantly removing from the beginning. We'll stick with 0 the entire time. Let's check this output out. A, B, C, and then you can see the rest of the list there. So the first 3 elements were removed, A, B, C. We printed each one in turn. That is, we printed the label that accepted the element. We removed it from the list and then immediately bound it or associated it with a label, and then moved on, printed it, and then moved on to do that 2 more times. Finally, we printed MyList, and you can see that MyList is now a shadow of its former self. There's only 4 elements there, where there had been 7. We could go on doing this until the list is exhausted. And actually, when we look at the while construct, we'll see a good way of doing that. A while can allow us to continually remove elements until there's no list left. I'll show that to you I'll show that to you in another video. So that's removing an element. What do we have left? 2 other operations that I'd like to show you with lists. And these are operations a little like Subscript or in particular for that allow us to, let's see how far I can go back with this, that will allow us to work in the same way with different types of containers. One is len. The other is in. Why don't I put this first? Okay, let's take a look at this code. MyList equals these 7 elements. If we look at the length of MyList, we'll see that it is, well, we have to save this first. Oops, we see that we get an error. Let's look at our error. Name Meister is not defined. Okay, that should be easy enough. Let's find Meister. Ah, Meister was not defined. Okay, let's do that then. 7 and A is in MyList. Let's take a closer look. 7 and A is in MyList. So what are we looking at here? Well, we asked for the length of MyList, and there are 7 elements. So we printed len MyList, and we got back 7, an integer object. We could also, of course, assign that to a variable. We could even give it a nice, of course, since it's an integer, we're going to have to stringify it. Take a look at that. Length is 7, and A is in MyList. Notice that if Z in MyList did not succeed, it was not true. Z is not in MyList. So this statement did not print, but A is in MyList, so we saw this print statement. And then also we used a len. Now len and in are also common to different containers. Tuples make use of them, dictionaries, and strings all make use of len and in. It's one of the simple features that's consistent across the language that makes things easy for us as programmers. So that is the list container.